This video is on dynamic memory allocation. In order to talk about dynamic memory allocation, I'm going to have to talk about memory regions first. There are 4 different regions in a program's memory usage. First, we have the stack. The stack is where all your local variables that you create in any of your functions go. And the parameters are stored here too. This is also called automatic memory and typically has high memory addresses. So that's why whenever I print out memory addresses, when I'm running our programs, I typically see a really high memory address there. And it's because those variables were created in the stack. The next section is called the heap. The heap is the largest part of memory, takes up the largest part. And this is the region where the new operator allocates memory and delete operator deallocates memory, also called free store. This is the part of memory that we're going to be talking about in this specific module. We're going to be dynamically allocating new variables, and they're going to go in the heap, where we can take up a lot more space if we need to. Then there's another memory region called the code. Code is where your program instructions are stored. And then the last section is global and static memory. These global variables and the static local variables are stored here, and they have low memory addresses. Okay, so there's a new operator called new. This new operator is what allows us to dynamically allocate memory. What dynamic memory allocation is allocating storage for a variable while the program is running. The computer returns the address of the newly allocated variable. We use the new operator to allocate memory. And so if I were to say new double, that would create a double variable in memory. Now, the only problem with that is that I now have this double variable. If I just look at this side of the equal sign, I now have this new double variable, but it doesn't have a name. So the new operator also returns the memory address of this variable, which you can then store in a pointer. So in this example, I created D pointer, and then when I created the new double, D pointer points to this variable. And now that is my name of this variable. It's just when I access the variable, I'm going to have to dereference D pointer. Normally you don't just dynamically allocate a single variable like this though. What's way more useful is if you can dynamically allocate an array. This is more useful because this means that you don't have to automatically know the size of the array when the program begins. You could technically get the size from the user. Now in this example, I did create the size in a variable that's a constant just for demonstration purposes. So what this part of the line will do right here that I've boxed in is it will dynamically allocate a new array that is 25 elements. And then, and each of these elements are doubles. And then the new operator returns the memory address, which is then placed inside of the pointer called array pointer. So this is assuming that array pointer was already created and it's allowed to be a pointer to a double. So array pointer is now the name of our array, and it's the only name that we have. So whenever I want to actually access these array elements, I have to go through array pointer. And I can either use array notation or pointer notation. Anything that you create with the new operator will not be deleted for you. So let me back up for a second. Whenever you create variables in your program, just local variables, I'm going to back up, they always go in the stack. And then whenever the program ends, those variables get removed from the stack for you automatically. That's why this is called automatic memory. But whenever you dynamically allocate something in the heap with the new operator, that stays there until you manually delete it. Which means you could potentially, if you forget to delete it, it could be there forever, or at least until you reboot your computer. So in order to release that dynamically allocated memory, we have to use the delete operator. You only use delete on anything that you created with new. And the syntax of this is we say delete, and then we put the name of the pointer that actually points to this dynamically allocated space. This is what it would look like if you were just releasing a single variable. But if you're releasing an entire array, you have to say delete, and then you have to have empty square brackets. There's no space in between those square brackets, and then the name of the pointer that's pointing to that array. I'm going to show you these two programs in a minute, but I first want to talk about what a memory leak is. I'm sure you've heard of memory leaks before, but a memory leak is caused by a program that allocates memory with new, but then loses the ability to access that memory. This is caused by failure to properly destroy or free dynamic memory. Memory leaks can result in slower program runtime, less efficient, simply because you're taking up a lot more space in memory, and it could potentially cause your current running program to fail. Okay, this program has a pointer that is allowed to point to a double, and it's called cells. So I'm going to draw cells as a pointer variable, and then we also have total, which is an accumulator. It starts out at 0, and we have average, and we have num days, and count, and those are not initialized. Then I print out cells. This isn't necessary. I probably just printed it out to show what that memory address, what it holds at the beginning, which is just junk data since I did not initialize cells to null pointer or null. Then I ask the user, how many days of sales figures do you wish to process? And we read that into num days. So let's say that the user enters in 3, just so we can go through an example. Then on line 32 is where we actually dynamically allocate a new array. What's the size of the array? It's based off of what the user entered. So in my example, the array is 3 elements. And this array is allowed to hold doubles. Then the memory address of this array gets placed inside of cells. So cells is the name of our array. We can then use either pointer notation or array notation to actually allow the user to enter in each of the cell values in this array. To keep it simple, I'm going to enter in very small numbers here. 14, 7, and 3. All right, after this loop ends, we will then get to this for loop right here, where I am adding up each of these array elements. And so we're going to keep adding up the array elements and placing it into total. So we're getting a running total. I think this is 24. That might be wrong, but we're pretending that it's 24. Okay, and then we calculate the average. And so we would divide 24 by 3. And place that in average, and then we would print out the total and the average. And then most importantly, we would then delete cells. Okay, so we have the delete operator, we have the empty square brackets and the name of the actual pointer that points to this dynamically allocated array, and that will remove that array from memory, from the heap. And then it returns 0 is when all the other local variables, which were created in the stack, get deleted. And so they all go away. Okay, so that's dynamic memory alloc 1. Let's take a look at dynamic memory alloc 2. We have a function in this one that we send an integer to the function, and look, it returns a pointer. Now, I've shown an example where a function returns a pointer in a previous video, and I said that that wouldn't work. Well, this shows you an example that will work. Okay, so in the main function, we have numbers, which is a pointer, and it can point to an int or an int array. Then on line 22 is where we call get random numbers, sending 5. 5 is passed by value, so a copy of that gets placed inside of num, which is down in a function. We have num, which has 5 in it. And then in this function, we also have a pointer called ARR. And then we check to make sure that num is not less than or equal to 0. It's not, it's a 5. So then we move on to line 47, where we dynamically allocate an array of 5 integers. And then the new operator returns the memory address, which gets placed inside of ARR. So that's the name of our array right now. Then I seed a random number generator, and then I have a for loop that will generate a random number at each iteration and place that random number in the array at, and this is using pointer notation. And so this is going to fill up the array elements, all 5 of them, with random numbers between 0 and rand max, which on my machine is 32,767. Then look, we have a return statement. What are we returning? We're returning the memory address inside of array, which is the starting memory address of this array. That memory address gets returned back right here where we called get random numbers and gets placed inside of numbers. And so it creates this connection. Now let's back up for a second. What all gets removed whenever this function ends? Well, all local variables to this function. So that includes count, which I didn't draw, but it also includes num, so num is gone, and it includes this pointer. However, this array does not go away, even though it was dynamically allocated here in this function. It doesn't go away because it was created in the heap, and data in the heap persists until you take it away. And so when we go back up here, this array still exists, and we can successfully grab the memory address from the function because it returned it. Then I have a for loop in the main function that will print these values out in the array using this for loop. And then I'm done with the array, so I'm ready to release the array. Typically, no matter where the array was dynamically allocated, you are always going to release it right before return 0. Since it's an array, I have to have the empty square brackets and then the name of the pointer that points to the array. So that's going to delete the array, and then at return 0 is when the program ends and all variables that were in the stack, which were created locally, are removed.